Welcome to the optics course. So, what is optics? Optics is the science of light. And what is light? Well, we all seem to know that answer, right? But let us start with the history of light first. Thousands of years ago, humans have asked some historical questions about light. The questions were very simple, but the answers were very hard to find. For example, what is light? What is its nature in particular? Does it act like a particle, or does it act like a wave? Exactly how is light created, and how fast does it travel? Whether the speed of light is finite in quantity or infinite. That is, does it travel instantaneously to everywhere? Intromission versus emission. A question that may seem very silly today, but actually was a very big question then. According to the intromission theory, light enters from external objects to our eyes, which is very much obvious to us today. But back then, most of the people believed in the emission theory, which tells that light is emitted from our eyes. And also, speed of light was a major point of argument. Nearly 2,500 years ago, Empedocles argued that light was some object in motion which takes time to travel. He was a big proponent of the emission theory. The likes of Plato, Euclid, and Ptolemy also had similar ideas. Although Euclid argued that light has infinite speed. Actually, he had a solid reason for this kind of thinking. He said, whenever we open our eyes, we see the stars immediately. Well, it's a good trivia actually. Can you explain his observation by using the finite speed of light that we know today? Okay, so let me share an interesting fact with you. In a survey of college students in 2002, it was found that a good number of students actually believe that light is emitted from our own eyes. That's surprising, isn't it? Now, according to the opposite of the emission theory, that is the intromission theory, something enters in our eyes which is representative of the object that we see. Eventually, it was Alhazen who, in his book of Optics, argued extensively against the emission theory. He also said that light has a finite speed and it slows down in denser mediums. Even after 600 years of that, two contemporaries, both Descartes and Galileo, actually argued against the finite speed of light. Descartes believed so because he saw there was lack of time delay between the shadow on moon and other background stars during a lunar eclipse. But the thing is, there was a time delay. It was only 1.2 seconds that he couldn't measure. And Galileo set up an experiment flashing two lanterns 1 mile apart and saw no delay between them. Actually, there was a delay, but it was only 11 microseconds that he couldn't measure. In the year 1676, Roemer qualitatively measured the speed of light to be 220,000 kilometers per second. And within a couple of decades, it was refined and well accepted as 300,000 kilometers per second. So the issue of speed of light got resolved in the 17th century. But to explain the optical phenomena discovered back then, there arose another critical question. Is light a particle? Or is light a wave? One of the biggest proponents of the particle theory was Sir Isaac Newton himself. He thought light as a particle because light did not bend around obstacles like wave does. Although using this particle theory, Newton explained reflection and refraction, but it had some major issues. According to Newton's corpuscle theory, light should travel faster in denser medium and slower in lighter medium, which is exactly the opposite of what we see in nature. It also could not explain the phenomena like interference and diffraction. Playing this phenomena came the wave theory of light. Huygens was the first person to fully work out this wave theory. Huygens explained the optical phenomena like interference and diffraction by using his wave theory. But he predicted that light is a longitudinal wave. And he correctly predicted that light should slow down in denser medium. In 1807, Young introduced his famous double-slit experiment, which actually supported the wave theory of light. In his experimental setup, he had a slit like this, then two slits after that one slit, and after that he had a black screen. Now, as light from a source enters through the first slit, it splits into the second two slits and then interferes with each other and creates a pattern like this, which can only be explained if light is a wave. This experiment was conclusive enough to say that light is actually a wave, and the different colors of light that we see in our everyday life correspond to the different wavelengths of light. Fresnel agreed with the wave theory of light and argued that light is a transverse wave, and this helped to explain the polarization property of light. So by 1820, the things we already knew was that light is a wave, and it is actually a transverse wave. Different colors of light correspond to different wavelengths of the waves. Light travels at 300,000 kilometers per second. It slows down in denser mediums. Snell's law of refraction, the double-slit experiment, polarization, all the phenomena are explained by this wave theory of light. But there is a big but here. If light is a wave, then something must be waving. That is, light needs a medium. And what is that medium? In comes the idea of the luminiferous ether. It is a hypothetical medium that was introduced to solve the problem of the medium of light. But light can travel everywhere, so ether needs to exist everywhere. From the inside of the atom to the furthest of galaxies, ether needed to be everywhere. It also needed to have some extravagant properties, like it must be frictionless, otherwise the planets would slow down due to its friction. It had to be massless too, otherwise the Kepler's law of orbital mechanics, which depends on gravity, would fall too. It had to be solid enough to support a transverse wave like light, because fluids and gases can only support longitudinal waves. In comes the electromagnetic theory of light. In 1861, James Clerk Maxwell conjectured that light is fundamentally electromagnetic in nature. That is, it is an electromagnetic wave. Maxwell, in his famous four equations, unified electricity and magnetism, which in turn gave rise to the electromagnetic wave. And this electromagnetic wave propagates at the speed of light. But the idea of unrealistic ether still did not end. In fact, it became more magical. Instead of being solid, it was imagined to be fluid in order to fill all of the space around, but a million times more rigid than steel to support the transverse waves like light, massless and frictionless like before, and still the relative movement would imply different speeds of light. In their experiment in 1887, Michelson and Morley showed that there is no change in the speed of light as the Earth moves around the Sun, even at different times of the year. But if ether was there, the speed of the light had to be different, which was not the case. So finally, it was the death of the ether, and the idea of the ether went to the graves. The final nail in the coffin of ether came with Einstein's theory of special relativity. You heard about the time dilation and length contraction stuffs, right? It's a good time to refer to the movie Interstellar. Einstein also explained the photoelectric effect, and for that he needed to consider that the energy of light is quantized. That means light acts like a particle. So it means we are back to the particles again. Okay, so what is the modern view of light? In the 1950s, Sir Richard Feynman et al., using electromagnetism and energy quantization, worked out a new theory of light which we call the quantum electrodynamics, or QED in short, and it is one of the most accurate theories that we have produced in physics. In this theory, photons are the carriers of the electromagnetic forces between charged particles. They are the bosons. These photons are the quanta of the light waves. So ultimately, we can tell that light are a collection of photons which has both particle and wave nature. This is known as the famous wave-particle duality. This is the brief story of light, at least for now. Thank you.